Hello and welcome to this video in which we show how to compute shear and moment diagrams for beams that are loaded with distributed forces. And to do this we'll use the relationship between shear and moment. That is, that moment can be expressed as the integral of shear, or shear is the derivative of the moment, but we'll actually use the integral part. So here we have an example. We have our yellow beam of sunshine or happiness or whatever you want to call it. It's just very yellow. And it has a distributed load on the top, which is 1,667 newtons per meter. It has a distributed load on the bottom pushing up, which is 1,000 newtons per meter. And what we want to do, again, is find the shear diagram, the function v of x, and the moment diagram, which is the function m of x. To do that, we will introduce what's called a weight density. We'll call this w of x. And this basically just shows the load on the beam as a function of x, where we start off here with x is equal to 0, and we go out here with x to 10 meters. Okay, so it just shows this loading per meter on the beam as a function of x. Now the thing that you need to understand, we call this again the weight density, and this is positive downward. So unlike other videos where things that point up I call positive and things that point down I call negative, this Wx is positive downward. That's because this generally represents some load on a beam, such as gravity or something like that. And if you're talking about a load, it typically makes sense to think of it as being positive downward. Okay, so the first thing we'll do is we'll find Wx, and then it turns out, we'll write out the important relationships here. V of x will be the integral from 0 to x of minus w of x prime dx prime. And if these primes bother you, we'll go through that in a little bit of detail, hopefully. And then we have the moment of x, or at x, is the integral from 0 to x of v of x prime dx prime. We'll use these relationships to get the shear force and the bending moment for this beam from this density, the loading density or the weight density. And in order to do that, then we need to have w of x. Once we've got it, then we've got the formulas which we can use to compute the other things we need. So for x between 0 meters and 2 meters, so if I choose some arbitrary point here between 0 and 2 meters and call this x, w of x is just going to be this 10,000 newtons per meter pointing up, which again, because w of x is positive downward, this will be minus 10,000 newtons per meter. Okay, that wasn't so bad, was it? If I now look at x somewhere between 2 meters and 8 meters, then we'll have w of x. We have the 1,667 newtons per meter pointing down. And then we have the 1,000 newtons per meter pointing up. So for x between 2 meters and 8 meters, our weight density is 667 newtons per meter. And finally, for x between 8 meters and 10 meters, so we choose a value of x out here, we have the same situation as we had between 0 and 2 meters. So w of x is minus 1,000 newtons per meter. Okay, so now we've got W of x. It's a function of x. We can actually plot it, and if we do, we get that W of x looks like this. For x between 0 and 2, it's minus 1,000. X between 2 and 8, it's 667. X between 8 and 10, it's minus 1,000 again. So that's not so bad, right? The next thing we need to do is we need to find v of x. And I'll rewrite the formula. It's the integral from 0 to x minus w of x prime dx prime. So what this means is you can think of me changing the variable in w of x. Rather than calling it x, I'll call it x prime. And I can do that because I can call the dependent or the independent variable whatever I want, and I have a function of this independent variable. The reason I do this is because v of x, what I'm going to want to do is, for example, choose some value of x that would be here. And then I need to find the integral from 0 to that value of x of minus w of x prime dx prime. So in other words, I have to find the integral from 0 to x of this function and take the negative. And so the function that in any case, the integral from 0 to x is going to be the area in under wx prime. In this case, that's going to be negative because it's minus 1,000. But so the idea is that I'm going to get this area, and then I'm going to change the sign of it, and that'll give me v of x. So conceptually, that's what we're doing. Now, I'll try to actually write this out in terms of the integrals to make sure that it's clear mathematically what we're doing, but that's the concept behind what we're after. So if x is between 0 and 2 meters, I have then that minus w, we'll have v of x. It's the integral from 0 to x minus w of x. Well, w of x is minus 10,000 or minus 1,000. So minus w of x is 1,000 newtons per meter dx prime. This 1,000 newtons per meter is just a constant, so I can take that out of the integral. And I have then 1,000 newtons per meter times the integral of dx prime is just x prime, so I plug in the limits, and I have x minus 0. And the minus 0 part doesn't do anything, so I can get rid of that. So for x between 0 and 2 meters, I have v of x is 1,000 newton meters times x. Okay. Pretty good so far, eh? So the next thing we want to do is look at a value of x that's between 2 meters and 8 meters. Okay. So we have 2 meters less than x less than 8 meters. And in this case, v of x will be the integral from 0 to x of minus w. I'm going to break that into two parts. I'll have the integral from 0 to 2 of minus w of x prime dx prime plus the integral from 2, this should be 2 meters, 2 meters to x of minus w x prime dx prime. Okay, well, I know from my computations up here that the integral from 0 to 2, which is what I have here, this guy is just v of 2 meters. And from my expression up here, which applies in some sense at 2 meters, I have this will be 10,000 or 1,000 newton meters times, well, here we'll write it out. This is 1,000 newton meters, newtons per meter, I'm sorry, should be newtons per meter, times 2 meters, which is 2,000 newtons. Okay, so this term up here is going to be 2,000 newtons, leaving me with only this term down here. Between 2 meters and 8 meters, minus w of x prime is going to be minus 667 newtons per meter. So I'll work this guy over here. This is going to be the integral from 2 meters to x of minus 667 newtons per meter dx prime, which is going to give me then minus 667 newtons per meter x minus 2 meters. Okay, so that's what this guy here is. And so if I add these two, if I work out what this is and add these two, then I get v of x is equal to 3,334 newtons minus 667 newtons per meter times x. Okay, so far so good. Now we need to find v of x. Let's see, where's a nice color that will show up? Over here. Okay, so we'll have a value of x over here. Let's see, we'll actually just do this on a new sheet. Okay, so we'll have v of x. This is the integral from 0. Well, actually, I already have that written down. So we'll write this as the integral from 0 to 8 meters of minus m of x prime dx prime, which hopefully you recognize this now as v of 8 meters, plus the integral from 8 meters to x, and between, well, of minus m x prime dx prime. Okay, so v of 8 meters is going to be, if I've computed this right, 2,664 newtons. And this is going to be minus m is going to be 1,000 newtons per meter times x minus 8 meters. And when you add these guys all together, you get minus 10,000 newtons plus 1,000 x. Okay, so that's v of x. And this again is for x between 8 meters and 10 meters. So I think I have plotted this. Yes, I have, surprisingly enough. And you can see that as x starts at 0 and goes up, it goes up with a slope of 1,000 newtons per meter. Then it goes down with a slope of minus 667 newtons per meter, and then goes back up with a slope of 1,000 newtons per meter. Hopefully it's clear to you that the slope here is given by this value, so that dvx dx is clearly equal to minus w of x. And again, v of x is the integral of minus w of x. So that will end part 1 of this video. Stay tuned for part 2, in which we find the bending moments.